and practice completing some nuclear reactions. So these reactions, you'll notice, like, I think about 3 of them are ones that we specifically looked at on whatever that was, Tuesday. The other ones are not, and so I want to see if you can complete the reactions even with nuclear reactions you may not know. Because remember, all you've got to do is add up the numbers and make sure they balance on both sides. So even if you don't necessarily know what the letter should be or what the type of reaction is, if you use the numbers, you should be able to complete the equation. All these last 4, for instance, in this 5.21, these are these bombardment reactions. We didn't talk specifically about those, but that's just when one particle hits, one nucleus or particle hits a nucleus and then forms something new. So again, those are different kinds of reactions, but if you just add up the numbers, you should be able to still complete them. So see if you can complete these 9 or so reactions. Don't worry about describing the types of radiation. We'll talk about that later, but see if you can complete these reactions as a review from Tuesday. And we'll go on from there. Maybe I have to get stuck on one of them. Take a couple more minutes and then we'll continue.
Is that okay like that? It's not going to fall. Okay.
All right, so let's take a look at some of these. We're going to go through all of them. We've seen some. Just looking at this first one, so we can see there's carbon on the left, 6, 11, so this is carbon 11, boron 11, and then what's left over is something with a 1 charge, plus 1 charge, and no mass. So that particle is not one that we have really talked about. That's called a positron. It's the opposite of an electron. It's a positively charged electron. But you could still get that, even if you didn't know what that was. All right. So we can see some of these. Another one I want to look at, just because it's a common mistake, is the next one, B. Note that this, what kind of emission is this? B, the next one over? Yeah, this is a beta, this one here. This is beta elimination, or I'm sorry, beta emission, because we see the beta particle here, right, the electron coming out. So the one thing that I see common mistake there is not dealing with that -1 properly. So we have to remember that in the beta emission, a neutron turns into a proton and releases an electron. So that means that the bottom number is going to go up to 17. The top number stays the same at 35, and that's chlorine. So please take note of that sign. Whether it's -1 or +1 makes a big difference. All right, and then we'll skip the rest of those. Are pretty straightforward unless there's questions. Looking down at these bombardment reactions, neutron bombardment is when you shoot a neutron at a nucleus. We're going to see this again in nuclear fission later today. And in this case, you're making a heavy version of that particular nucleus. So instead of beryllium-9, we now have beryllium-10. Sometimes neutron bombardment results in another particle coming out. And that's what we see here is in B, it's kind of like neutron bombardment followed by beta emission. So what's left there is, if we have to total these up, so that's 132, and the total on the bottom is 52. So that means the totals on the other side have to be the same. So that means that our question mark here, I'll write it over here for space, needs to be 53 and 132. And that's iodine. Do you see where those numbers come from?
Why we added because the minus?
Right, because the beta particle. So what's really happening there is the neutron bombards into the nucleus, breaks into a proton and an electron. The electron comes out as a beta particle. The proton stays there. So the atomic number has increased, and then the mass is increased by 1 from the neutron coming in. C is neutron bombardment followed by alpha emission. So the neutron comes in, the alpha particle goes out. If we add the particles on the right side there, it's a mass of 28 and a number of 13. So 13 and 28, but we don't write 13, 28 over here. We're going to write 13 and 27 because there's already one here in the neutron. So the sides have to balance total from all the particles on each side have to balance out. So that ends up being aluminum. And then finally, something we haven't seen at all, releasing a hydrogen nucleus. So you've got an alpha particle bombarding a nitrogen nucleus, and then a hydrogen nucleus coming off and something else ending up there. If we just make sure the numbers all add up, we should be fine. So that's 9 on the bottom and 18 on the top on the left side. If we want to do that here, that means we have to do 8 and 17 so that those can add to the 1 and 1. So that would be oxygen 17.
How about number D, the first one?
Yeah. So that's alpha emission. Right? So both sides need to add up so that we've got 83 on the bottom and 210 on top. So that means what is left over here is going to be 81 and 206. Thallium, TL. All right, so that's the nuclear equations. Now, while we're talking about this, I'm going to skip a little bit in the book, but we'll come back to it. Let's look at nuclear fission and nuclear fusion while we're talking about these types of reactions. So you've probably heard of nuclear fission. That's the reaction in a nuclear power plant or in a nuclear bomb. This is the splitting of the atom that we often think about, or when we are talking about radioactive things, nuclear chemistry. And we're going to talk about exactly what's happening in that reaction and why it's so important. Rather than writing it out here, I'm going to copy the picture from the book so we can really see what it looks like. If I can find it, there it is. So here's our nuclear fission reaction. I'll copy it into the notes. And then we've got kind of a picture of it, and then what the reaction looks like on paper when we write it. Okay, so you have a uranium nucleus. Uranium-235 is a fissionable nucleus, which means that when it is bombarded with a neutron, it can split apart and undergo this reaction. Most types of nuclei can't do this. Even most types of uranium nuclei can't do this. If you look at uranium on the periodic table, number 92, it says the mass is 238 point something. The most stable nucleus of uranium is uranium-238. That's the most common nucleus of uranium. So most of the uranium in the world is uranium-238 and can't do this. But a little bit of it is uranium-235, which is fissionable. So when we talk about enriching uranium, or like governments needing these special centrifuges to enrich uranium, that's what we're talking about, is separating out this very special uranium that can do this reaction from the rest of the uranium that cannot. You have to be able to separate things whose masses are very, very close, and that's why you need some kind of technical equipment to do that. So when you take this uranium-235, it's bombarded with a neutron, which makes it unstable, makes it uranium-236, and then it breaks apart into two relatively large nuclei, barium-142 and krypton-91. In doing that, it releases 3 neutrons. Now, there's more to the story here. Fission can also produce other things. There's various pathways it can go. This is kind of a common, basic textbook fission reaction. So a couple of important things about this. First of all, when that nucleus breaks apart, it releases an enormous amount of energy. That's why we see this as a useful reaction, enormous amount of energy. Furthermore, the reaction also results in more neutrons being formed. And that allows this to happen as a chain reaction. So a normal nuclear reaction might be a nuclear bombardment, like the ones that we saw in those practice ones a little bit earlier. You'd bombard something with a neutron, but then you just make something new, and you're done. In a fission reaction, you bombard with a neutron, it breaks apart, and then it makes more neutrons that can go and break more nuclei apart. And that's why it's called a nuclear chain reaction. So there's a little picture of this, I think, in the book too. Yeah, here. I'm not going to copy this whole thing over because it's a big figure. But this is a depiction of what that might look like. So if every neutron that is involved, that is expelled from the fission reaction, goes on to create another fission reaction, suddenly you have a whole bunch of stuff happening. And this all happens very, very quickly. And because of this self-sustaining nature, this is why this works in something like a bomb, that all of this nuclear fuel in there can very quickly, all of that energy is very, very quickly released. In a nuclear power plant, this is also the reaction that's happening, but the reaction is controlled by these what's called fuel rods, so the uranium can be removed from the reaction or put back in the reaction depending on how much energy you want to come out. So the reaction is more controlled that way, and so that allows us to not let it run away and create too much energy. All right, so we look at the reaction the way that we would draw it, or the way that we would write it. It's kind of like these neutron bombardment ones. The neutron reacts with the uranium, and sometimes this middle part is not even shown, just the products, which are these things. And if we add all this stuff up, it does add up. So 236 on top, 92 on the bottom. 36 from 56 plus 56 is 92. And then we've got 91 plus 142 plus 3 for the 3 neutrons. Comes out to 236. So that one balances as well. Nuclear power in a power plant is probably something we should be talking more about as a society, especially with climate change and that kind of stuff that's going on. It's not a fossil fuel, so it does not produce carbon dioxide when it undergoes this reaction. It takes a very, very small amount of uranium to create an enormous amount of power. So you don't have you don't have to ship massive amounts of fuel like you do with a coal-fired power plant or something like that. This is used to heat up water, which then turns the turbines. Basic steam turns the turbines. So there's very little waste, but the waste that is produced in these kinds of reactions is radioactive. So the waste from a nuclear power plant needs to be really carefully disposed of. Essentially, it needs to be locked underground where no one can ever get to it. And that can create some problems if there's a large-scale adoption of nuclear power. Where do we put all this waste? It's not a lot it's not that much by other standards. I mean, it would all fit, inside a mountain or something, but there still is that issue of what do we do with this waste? Where do we put it to make sure that it's safe, that it's isolated from people, from animals, from plants that are not going to be affected by the radiation? Because even after the reaction's all done, the products are still radioactive and are still releasing different kinds of ionizing radiation. So that needs to be, well, there's a lot of issues with that, like shipping. So if you've got a nuclear power plant here in Illinois, as we do, and we want to store this waste in a mountain in Utah or something, well, that radioactive waste has to be transported across the whole country. And then you have the various exposure issues associated with that if train crashes or something. So there's a lot of things to think about in radioactive waste disposal. Another type of nuclear reaction that is important is called nuclear fusion. Now, fission, that word fission, what we talked about before, is about breaking things apart. Fusion is about putting things together. So in nuclear fusion, we take something like radioactive hydrogen, hydrogen-3, also known as tritium. You take 2 of those and basically smash them together. It creates a helium nucleus. And a neutron. And a lot of energy. In fact, more energy than nuclear fission by mass. This is the world's most efficient reaction in terms of energy production. This is how the sun works. The sun does a pretty good job as far as like keeping us alive and all that. So this is what's going on inside the sun, other stars. Enormous amount of energy is released by really small things. And when you have very small things releasing a lot of energy, that's very efficient mass-wise. You don't need a lot of mass. So why don't we just do this for our energy needs? Anybody know? You also don't make radioactive products with it. Well, some, but why don't we just do some of this and then solve all our problems? Anybody know? It's a temperature thing. This only happens above, and I'm estimating here, above about 100 million degrees C. That's pretty high temperature. So the problem with nuclear fusion is you need so much energy to get to 100 million degrees before you can even do the reaction that it becomes inefficient. And you have to use so much energy to put in that you don't get enough energy out to make it worth it anymore. So that's why we don't use fusion as an energy source, although you could argue that solar energy is really a fusion energy source because we're getting it from the sun, which is getting its energy from nuclear fusion. We can do this. If you've heard of a hydrogen bomb, that's a fusion bomb. And in that situation, it's actually both things together. It's a fission bomb, a uranium bomb, that creates enough temperature, enough energy to then start this going. So it's actually two things together, which is a huge amount of energy and difficult to control. So there's a lot of interest in this. Whether it's something we can ever actually do on Earth in an efficient way, it's called cold fusion. It's probably not likely, but there are a lot of conspiracy theories about it. A lot of people think that the government knows how to do this and they're just keeping it secret from us, those kinds of things. Probably not. Every now and then someone comes out saying that they've figured out how to do nuclear fusion at low temperatures, and they're always wrong. Maybe someday. All right. So let's talk about, we'll go back a little bit now in the chapter. We've got two more topics to look at with nuclear chemistry. One is measuring radiation. How do we talk about radiation, exposure to radiation, that kind of thing. And then we're going to use that when we look at how things break down over time, which we call half-life. Okay, so first, measuring radiation. I just want to show you a couple of units. There's two ways we can measure radiation. One is how much radiation is emitted. So I've got a radioactive substance. It's emitting radiation. How much is it emitting? And the units we use for that are the Curie and the Becquerel. We're not going to go into all the specifics of what the numbers are for each of those, but if you hear something about Curies or millicuries or kilocuries or becquerels, those are microbecquerels. Those are units of radiation. So that's how many particles are coming off of a radioactive substance in a given amount of time, usually. Like one alpha particle per second or something like that might be one of these. So we're going to look at that when we talk about half-life. But one of the ways this is really useful is if you think about things like radiation therapy or nuclear medicine. You want to know exactly how much of a dose of radiation is somebody's getting. So if this little pill of radioactive whatever has 99 millicuries of radiation, then you know that's how much to use. So that's where those numbers come in. And then the second part, which we encounter more in our lives probably, is exposure. How much radiation is absorbed? Like for you, how much radiation are you getting? If you're somebody who works with radioactive substances, or you work with even things like X-rays, you'll probably wear some kind of a monitoring device so that an organization can check, something like OSHA can check, how much radiation are you getting? Are you getting too much? Are you getting a safe amount? That kind of a thing. So people who work in hospitals, as radiological technicians, or anybody else who's working with a lot of that stuff, nuclear medicine technicians, might wear monitoring devices like a ring, if you're using your hands, or a badge, something like that, that's checking how much radiation you're getting. And that's going to be measured either in rads or rem. And I'll put a little highlight here. Rem is the most common unit for humans, because the rad is a radiation absorbed dose, like literally just how much radiation is a certain amount of material getting. But rem kind of standardizes that for people, so that some radiation is more dangerous to people than others. So rem standardizes that across the board. 50 rems of radiation is the same no matter what kind of a source it is. So the average amount of radiation that a person gets per year is about 360 millirem. So 1,000 millirems in a rem. The average person gets about 360 millirems in a year. Now, where does that come from? Lots of different places. It comes from the ground, from radioactive elements in the ground. Even in building materials, bricks usually have some sort of radioactivity just because of the material they're made from. Cosmic rays, gamma rays from space come down and hit us, that source of radiation. When we get X-rays, CT scans, that kind of stuff, that's exposure to some radiation that counts in this. And then things like going on an airplane increases your exposure, because when you're higher up, you're closer to, there's less atmosphere filtering out all those particles from space, so more of that stuff is getting you. And depending on if you're getting chest X-rays or other types of things, that can go a little bit up or down, but that's just average for people. If you are getting close to 5 rem a year, which is 5,000 millirem, that's when it starts to become a problem. And that's kind of your upper limit for what's safe for a person for a year. So most people don't ever approach that amount at all. Things like living close to a nuclear power plant or living under power lines do not affect your exposure to radiation. There's not a significant amount of radiation coming off of those things. Cell phone towers would be another one. That's not an issue. That's not ionizing radiation. All right, so let's look at half-life then with the time we have left. Has anybody heard of this half-life before? Half-life is how we describe the decay of these particles, and it's a type of exponential decay, which means that it does not decay linearly. So if you have a sample of radioactive material that, let's say there is 10 grams of radioactive material, it's not going to decay linearly. So over time, it's not going to go from 5 grams to 4 grams to 3 grams to 2 grams to 1 gram over a linear period. It's going to drop quickly and then kind of even out, or I guess to you guys it's like this. And that's because each individual nucleus either decays or it doesn't. There's no partial decay for a nucleus. It either does the reaction or it doesn't do the reaction. And so that's how this is modeled. And the best way then to measure how long it takes for things to decay is through this concept of half-life. And the half-life is defined as the time it takes for 1/2
of a substance to decay.
That's the half-life. And it doesn't only apply to radioactive isotopes. Half-life is also used in medicine. When you take a drug, you'll often want to know about the half-life. How long does that drug stay in your system? And so the half-life is how long until half of that is gone, has been metabolized. And if you have things like instructions on medication to take every 6 hours, or don't take more than a certain amount in 24 hours, a lot of that has to do with this. How long does it take your body to process that and make it go away, metabolize it? So let's do an example and we kind of show how to do this calculation. Let's say you have we have 10 grams of radioactive iridium-192. The half-life, which is written as a T with a little 1/2, so time to get to half-life, is 74 days. So that means that every 74 days, half of that sample has decayed into something else. It hasn't just disappeared, but it's decayed into something else. And the easiest way, I think, to do problems like this is to just track it and just count it out half-life by half-life. So if we start with 10 grams, after one half-life, which is 72 days, we have 5 grams. You see how that works? Just cut it in half. After another 72 days, we have 2.5 grams. After another 72 days, we have 1.25 grams, and so on. We could keep tracking that. So if the question were how long until there's 1.25 grams left, how long until only 1.25 grams remain, until that's all that's left? You count it out and you say, okay, well, there's 5 grams after 72 days, 2.5 grams after another, which is 144 days, and then another 72 days is 1.25 grams. So that's going to be 3 half-lives. Which is 3 times 72, or 122 days. So this is kind of different from other calculations that we've done because it involves cutting it in half every time. We're not dividing by the numbers, we're just cutting in half that many times. So if I say how much is left after 3 half-lives, we don't divide by 3, we cut in half 3 times, which is different. So make sure you keep that straight when we're talking about half-lives, that you're always cutting it in half. Now, you can find out how much is in the in-between time, like in between one half-life after, 50 days instead of 72 days. That takes a little more calculating. There's an equation for that. We're not going to go through that in this class. If you want to look at it, it's in the book and whatever. But we're just going to deal with cutting things in half a certain number of times and trying to figure it out from there. You can also do this from the other side, which is the radioactivity. So let's say we have some radioactive sample and its radioactivity is 8 times 10 to the 4th becquerels. So that's the radioactivity. That's how many particles are coming off of this thing each second. This same thing, by the way. We're still talking about iridium 192. Looks like zirconium now. Iridium 192. So we're still talking about iridium 192. We have a sample with this radioactivity. And we can say what is the radioactivity after 148 days? We want to know how much has decayed, because the radioactivity is going to track with the decay. That is, when there's only half the sample left, there's only half the radioactivity left. So how many half-lives is 148 days? Whenever you see a problem like this, the first thing you want to ask is, how many half-lives is that? So how many half-lives for this particular isotope is 148 days?
74 days.
Is one half-life, yeah. So how many half-lives is 148? Well, if one half-life is 74 days, how many half-lives? Yeah, it's 2, right? 2 half-lives. (74) is 148. So that means to figure out how much is left after 2 half-lives, we have to cut that radioactivity number in half twice. So we're going to go 8 times 10 to the 4th to start. After 1 half-life, we've got 4 times 10 to the 4th. After 2 half-lives, we've got 2. So after 2 half-lives, that's how much is left. That's the whole, that's all there is with half-lives, but let's practice a bit. Look at some different ways to ask these kinds of questions and to work through these kinds of calculations. Oh, by the way, let's take a look at this table real quick while we've got it here. Half-lives can be all over the place. So here are some different kinds of isotopes. They could be extremely Laron, like this uranium-238. Its half-life, it's radioactive, but its half-life is 4.5 times, 4.5 times 10 to the 9th years. So 1 billion years.
So we will divide it by 2.
Well, however much we have, we will divide it by 2 after 4 billion years. Yeah. So that means that that stuff is not breaking down very quickly. But then something like this technetium-99m that's used in gamma imaging, that kind of thing, its half-life is 6 hours. So however much you have, 6 hours later, you have half of it. And so that means that facilities that use that often generate it on site, because you have to make it right as you need it, otherwise it's gone. Or you make a little more than you need, I guess. And then other things in between. All right, so let's take a look at some examples of these. organ scanning with technetium-99m. Says it's an ideal radioisotope for scanning organs because it has a half-life of 6 hours, which means it's gone pretty quickly, and it's a pure gamma emitter. So it releases these gamma rays that can be detected by equipment, but it's not bombarding your organs with other kinds of radiation that would be more damaging. So if you got 80 milligrams prepared this morning, how many milligrams would remain after the following intervals? So we start with 80 milligrams. And after one half-life, how much would be left? 40. Cut it in half. What about another half-life? 20. Third half-life? So you see how we're cutting it in half each time? This is, I think, the best way to do these kinds of problems. Set up a little map like this where you're just cutting it in half a bunch of times. Then see what the problem's asking and see where that fits in the map. So one half-life, that would be right here. Two half-lives is here. And how many half-lives is 18 hours? Yeah, that's 3. So that's C. And then how many half-lives is 24 hours? 4, right. So we go one more, cut it in half one more time. And that's D. All right, let's try one with the let's try with this one because it's a little bit more abstract, but you can still figure it out, I think. Strontium-85 for bone scans has a half-life of 65 days. How long will it take for the radiation level to drop to 1/4 of its original level? And then how long will it take for the radiation level to drop to 1/8 of its original level? How would you do a problem like that? This one doesn't tell you an initial amount, but it wants to know when will it get to 1/4 of its initial level. Well, I think a nice way to think about this is start with 1. We're not told the number to start with, so we can start with whatever number we want. So let's start with a nice easy one, and we'll just start with 1. So let's say we have 1 at the beginning. After one half-life, which is 65 days, what do we have if we start with 1? Yeah, we'll have half. So then another 65 days, we cut that half in half. What do you get if you cut a half in half? 1/4, right. And then what if you cut that 1/4 in half? Not quite. 1/8, right. If you cut a 1/4 in half, you get an 1/8. So now we have our little map here. So to 1/4 of its original level, it will take 2 half-lives, which is 130 days. to get to 1/8, we'll take 3 half-lives, which is 195 days. All right, let's look at some more of this. Now, here's another interesting question, where we're looking at a graph of the mass versus the time, so basically the half-lives. And it says, use the following curve to answer these questions. Complete the values for the mass on the vertical axis, and then complete the days on the horizontal axis, and then figure out the half-life just from the data in the graph. So let's see if we can do that. The looks like the things here are cutting in half each time. So 80 blank 20, what's going to go there? So you cut 80 in half, and we've got 40, right? And then 20, and then 10, and then 5. Ever see that? And then the x-axis is time, so that's going to be spaced evenly. So we've got 8, I assume, days, I guess. I didn't see the, should have moved it down. Yeah, days. So we've got 8 days, 16 days, 32 days, 40. Because that's not doubling, that's just... Oh yeah, wait a second here. That shouldn't be 32 then, right? That should be... Assuming these are all evenly spaced, this should be 24 and then 32, because those should be evenly spaced.
So the down will double.
Yeah, so what's the half-life then?
The half-life? 60.
How long does it take for the amount to be halved, to cut in half?
Oh, it will be 8.
Yeah, 8 days. Because in 8 days, it goes from 80 to 40. In 8 days, it goes from 40 to 20. In 8 days, it goes from 20 to 10, and then 10 to 5.
But the down, why we double? Only days, yeah? We double the days.
No, we double the mass. We only count the days up by 8, 8, 8, 8, 8. Or the days, yeah. And you're going to create a chart like this from in lab on Wednesday when we look at some nuclear isotopes. Right, we have lab Wednesday and then the exam is the next week. Is that correct? I think that's right.
We have an exam 3 on May 2.
Oh, so we have a few weeks until the exam.
May 2nd week.
Here May 6.
Okay. Yeah.
But if 2, we have on Wednesday, yeah?
Right.
The next Monday lab, next Wednesday exam 27th, April 27th.
No, the exam will be that week of May something.
Maybe.
So May 4th, I guess?
Yeah.
So next week.
Next week's lab, and then another lab, and then exam. Okay, so we've got a little time. All right, let's look at another
couple half-life type problems here. All right, the half-life of oxygen-15 is 124 seconds. If a sample of oxygen-15 has an activity of 4,000 becquerels, how many minutes before it has an activity of 500 becquerels? So going from 4,000 to 500. See if you can find how much time that is. So give that one a try on your own. And we'll discuss it. All right, you got this one, anything? What'd you come up with? 6 minutes and some seconds? Okay, yeah, that sounds about right. So to go from 4,000 to 4,000 to 500 is how many half-lives? 3 half-lives. Because you're going to go 4,000 to 2,000 to 1,000 to 500. So 3 half-lives. Each half-life is 124 seconds. So 5 times 124 is what you come up with? Sorry, say again.
1 times 124 by 3 instead of 5 because there's only 3 half-lives.
Oh, yeah, you're right. Sorry. 3 times 124, that's going to be 172. And if you divide that by 60, you get 6 minutes. Divided by 60 is 6.2 minutes. So that's 6 minutes and 12 seconds. Because 0.2 minutes is 12 seconds, a fifth of a second. Okay. Let's look at one more. Minutes left. I want to look at one about dating. Let's see. So here's one where we're told the time, but not the half-life. We have to find the half-life. The amount of radioactive phosphor-32 decreases from 1.2 milligrams to 0.3 milligrams in 28.6 days. What is the half-life? So now you've got a sample decreasing to a certain amount over a certain amount of time. Can you figure out what the half-life is? See what you can do, and then we'll talk about it. What do you think?
I don't know. I just
Okay, we'll talk about it in a second. So we want to set up the same kind of map in this case. We start with 1.2 milligrams, and then we're going to cut it in half, just like anything else, and see what happens. So that gets us to 0.6, and then 2.3, which is what's given. So in going from 1.2 to 0.3, we've gone through 2 half-lives. Yeah, and it says that time is 28.6 days. Yeah, so we would cut that in half. So this 28.6 days must be 2 half-lives.
So it's going to be 14.6.
Yeah, so that means 1 half-life is going to be 14.3 days. Everybody see where I got that? Questions about that? Okay. All right, that's it. So we'll have a quiz on this on Tuesday just on writing reactions and doing some half-life calculations. And that's it. So it should be a good quiz for everybody.
So on the reactions and those
hmm
calculation, and that's it.
That's it. Just the stuff from this week.
The reaction we did the green particles.
And from Tuesday. Yeah. So let me know if you have any trouble with it. I'll try to get all the grades posted next week or this weekend, so you have all your labs back. You can see it shouldn't really change much for anybody, but I will get those up there.